So continually we have to be get into that next episode. In the previous episode, we discussed how the SOM is mimicking the activities of that brain. And number two, the SOMs, it's having the very competitive learning by the measurement of distance, either by the Manhattan distance algorithm or by the Euclidean distance algorithm. It's making the highest computation, which particular node it's having the very closest to the previous one. So this is for that the competitive learning. And number three, this SOMs is mimicking it's with that cooperative learning. That means neighboring nodes that have adjust with the weights. So even in our brain is also store its data by the weights. The weights means the incidence. So what we had. So some moment in the childhood, we may driven by a street dog, or we might have certain encounter with the dog at that age of 3 or that 4 or that 5. Even at that age of 30, 40, 50 or 60 or 70, even in that moment we can able to be remember what happened at that age of that 5 in some time. So in that initial period, we may try to learn that bicycle. So on that very first time we may felt into the ground, and we may had that certain serious injuries like brushes or that certain bone damages. These events can able to be remembered even at the age of that 80s or that 90s. Reason is it's having that cooperative learning. So these are all the prime concepts behind that activities what's happened in the biological brain. The same thing that has been happened in that self-organizing maps also. So in self-organizing maps, we are having the three methods of working principle. That's number one, it can able to mimics the brain. That means the self-organizing like the sensory mapping. And number two, it's have competitive learning. So like the find out the distance between nodes and then capture which nodes that is very closest to the previous nodes. And number three, it's having that very cooperative learning. So the neighboring nodes can able to adjust with the weights. So these are all the prime concepts behind the SOMs. So now we have to be get into the architecture of the SOM. In previous episode itself, we discussed these architectures. That's number one is called that input layer. So already we said in that first episode, the SOM it has an ability to implement the dimension reduction. So the input layer may have the high dimensional data vectors. So what actually the neural networks has. So, and number two, we are having that is that output layer. So in that output layer, we are having the reduction. We can able to be extract that output in 2D or that the 3D. We are having that's a neuron grid with that appropriate weight vectors. In case if the input layer is having the multidimensional data, so after applying of that SOM, that output layer may have either the two-dimensional or that three-dimensional neuron grid with that appropriate weight vectors. And finally, the SOM architecture, it's having that's a neighborhood function. It has been called as that f of x. Either the Gaussian or that bubble can able to be implement the concepts of that neighborhood function. And now we have to be go with the how the SOM is working with that training algorithm. So that is the 4 steps we are having in the coconut learning. So that's one part of SOM. That is number 1 is called the initialization, and number 2 is called that is the computation, and then so number 3 is called that cooperation, and number 4 is called that is the adaptation. So initialization, so randomize that the neuron weights. Already we know how the weights that has been assigned in input layer. So initially we have to be go with the random weights, and then the random weights should be matched So according to the distance. So either by that Euclidean distance algorithm or by that Manhattan distance algorithm, and we have to be find it out. So which node is having that more competitively close. So this is called that is the best matching unit. It is called that is the BMU. So in the competition we have to be carried out the best matching unit. And number three, we have to be go with the cooperation. That means we have to update that best matching unit along with the neighbors. So we can able to be sequence that weight 1, weight 2, weight 3 according to that parameters with that interval of that so plus 1. And finally we have to be go with that adaptation that adjusts the weights according to the learning rate. So this is an iterative process, and finally the weights that has been adjusted with the wi of t plus 1, that is on the next node, next node, that's equal to wi of the t plus learning rate, that's called that is the alpha of t, and then so the h of t that should be multiplied with the old value of that is the x minus wi of the t. So that initial value of that is the t0. So that previous value that should be multiplied with that. So this will provide that is the new value of that. So wi of that t plus 1. So on that finally we have to be so look over what are all that main applications, the key features. So it may go with that the topological preservation, and it can able to be work with that unsupervised learning, and we can able to be go with that appropriate visualization. So SOMs is giving that very good outcomes so comparatively with that other techniques, and this SOMs can able to be implemented with the image compression and the healthcare and then some finance. So these are all that great applications of SOM algorithms. So thank you for stay tuned with us. Thank you.